So today we're going to look at collisions and conservation of momentum. So if you have when two bodies collide and there's an impact, during the impact there is a transfer of momentum. Some momentum, so if you've got one body here and it's moving, and there's another body here and it's moving, and they collide, and they then bounce apart. I'll call this U1 and U2 and V1 and V2, and there's going to be a transfer of momentum between these objects during a collision. When we consider a collision, we're going to be considering that that both objects are moving in the same line, and it's going to be a one-dimensional motion. Now, you may have seen a popular kind of toy called a Newton's cradle. It's something that often you'll see in movies on the desks of big executives, and you've got a ball at one end, and then you've got a series of balls all side by side. And what happens if you swing this ball, it collides with this, and then the momentum is transferred along, and then the last ball then swing out and come back and collide again. In a perfect Newton's cradle, it will look like the middle balls don't move. In reality, you'll see that they move a tiny wee bit, but you'll have this motion that looks like it kind of just keeps going back and forward, and that is that we see that because of the transfer of the momentum between each of the impacts on these little balls. Similarly, if you had a hammer, and when it hits a nail, there is a transfer of momentum from the hammer to the nail, and the nail then moves forward. And it won't move forward too much because obviously you're hammering it into something and there's resistance coming from the wood or whatever you're hammering it into. But that transfer of momentum causes this nail to move. Another obvious example is in the game of snooker. When you hit one ball, that ball then hits another ball, and this ball will then move. You've got that transfer of momentum. The transfer momentum, when the contact forces between two objects involved in the impact are equal and opposite, the momentum transferred from the first object to the second object is equal and opposite. So the momentum transferred from the first object to the first. This means that the total momentum before the impact must equal the total momentum after the impact. That doesn't mean that this object will have the same momentum after the impact as it did before. It means that the whole system, if you were to add the momentum of this object plus this object, and then add the momentum of this one plus this one, that total momentum is always conserved. And this is a really important principle in mechanics. The total momentum is unchanged. Momentum is conserved on impact. So when we've got some ball here with velocity u1, and then another ball here with velocity u2, and then the masses, obviously the mass will be unchanged for each object. The total momentum is m1 times u1 plus m2 u2. And then after the collision, well, the mass is going to be the same, but now this ball's going to have some new velocity v1, and this ball's going to have some new velocity v2, and the total momentum after is m1 v1 plus m2 v2, and those are equal to each other. So let's look at an example. Two balls are moving directly towards each other. The first ball bearing has mass 20 grams and is moving at 3 meters per second. The second has mass 25 grams and is moving at 1 meter per second. After the collision, the first ball is stationary. What's the speed of the second ball after the collision? So we split this question up into two parts. Think about the momentum before the collision. So we have our first ball, and that's travelling at 3 meters per second. Now note here, the mass is 20 grams. We have to write that as kilograms. So that'll be 0.02 kilograms. And the second ball bearing is moving at 1 meters per second, and that has 25 grams, which is 0.025 kilograms. Then after this is moving at 0 meters per second, and our second ball bearing we don't know, but the masses remain unchanged. So the total momentum before is equal to m1 u1 plus m2 u2. So it's 3 times 0.02 plus 1 times 0.025, and that's going to give us 0.035 Newton seconds. The total momentum after is going to be 0, because that's now stationary, plus v2 m2, and that must equal the same as before. And so v2 we don't know, and the mass is 0.025, and that must equal 0.035. So the velocity must equal 1.4 meters per second, because the momentum is conserved. Sometimes after a collision, so say we've got two blocks, and this one's moving towards that one, and that one's moving in that direction too. Sometimes after a collision, they come together on impact. We call this the objects may coalesce. This means they collide and they move off as a single object. Objects can be thought to have merged into a single object, and in this case, if this has mass m1 and this has mass m2, the mass of this object is going to be the two masses added together. Examples of this would be when a railway truck is pushed up to an engine and there's coupled with it, or a person jumping onto a moving vehicle, or if two ice skaters are meeting up and they hold and then when they come together, hold hands, and they continue as one. The opposite is true. The opposite is called an explosion. So when two objects at the beforehand are together and they're moving as one, and then they come apart. An example of this is when an engine and truck are decoupled, or if somebody jumps off a moving object, or if those ice skaters they do whatever they're doing, they're holding hands, and then they come apart and they dance off separately. That kind of situation would be an explosion. So let's look at a couple more examples. A girl is sitting on a sledge. The girl and sledge have a combined mass of 50 kilograms. When the girl and sledge are moving at 2 meters per second, her sister in front throws a snowball. The snowball has mass 0.2 kilograms and is travelling at 10.55 meters per second. The snowball and the girl and the sledge continue together. Find the new speed of the sledge. So we've got our before situation. So we have the sledge and we have the girl. And the mass here is 50 kilograms. And they're moving in this direction at 2 meters per second. And now we've got a snowball. And it has mass 0.25 kilograms and it's moving in this direction. Now, this is important when you're looking at these sorts of situations. If we think of this direction as the positive line of motion, the velocity of the snowball is going to be negative, and it's 10.55 meters per second because it's moving in the opposite direction of the sledge. After, we've got the girl and her sledge, and we've got the snowball, which wouldn't be a ball anymore, it would just be a lump of snow, and it's on the sledge and it's moving off in this direction with some velocity that we don't know, and the combined mass will be 50.2 kilograms because we've got the sledge and the girl plus the snowball. So let's look at the total momentum before. So we have m1 u1 plus m2 u2. So it's going to be 50 times 2 plus 0.2 times minus 10.55. So the total momentum before is going to be 97.89 Newton seconds. The total momentum after is the mass times V2, and that must equal 97.89 because of conservation of momentum. So it's 50.2 V2. So the velocity must be 1.95 meters per second. So the sledge was started at 2 with a 1.95, so it slowed down a little bit after the collision with the snowball. Let's look at one more question. A block of mass 200 grams is moving at 4 meters per second. It makes a direct collision with a larger block of mass 500 grams, moving at 1 meter per second. On impact, the blocks coalesce. Find the speed of the blocks after the collision if the blocks were initially moving toward one another. And B, find the speed after the collision if they were initially moving in the same direction. So let's think about the first situation before. So we've got these two blocks, and this one's going at 4 meters per second, and it has mass 0.2 kilograms. Remember, that's 200 grams. And this one, they're coming towards one another. Oops. And this one's coming with 1 meter per second, and it weighs more. It's 0.5 kilograms. And after they have some V, which we don't know, and they're stuck together. So the total mass would be 0.7 kilograms because they've added together. So the total momentum before is going to be, so the mass 0.2 times 4 plus 0.5 times, now it's going to be minus 1 because it's in the opposite direction. So that's going to give us 0.3 Newton seconds. So the total momentum after will be the total mass, 0.7, times whatever velocity that is, and that's going to equal to 0.3. So for the velocity is going to be 3/7 meters per second, and that's equal to 0.429 to 3 significant figures, meters per second. Now let's look at the other scenario where we have the first block, it's again moving in this direction with 4 meters per second, and it still weighs 2.2 kilograms. And this block is moving at 1 meter per second with mass 0.5 kilograms. And then after, we've still got them moving now in some other velocity we don't know, and the mass is 0.7. So the total, that's in that direction, momentum before is 0.2 times 4, add 0.5 times 1, and this time it's positive 1 because the direction of motion is the same. So it's 1.3 Newton seconds. The total momentum after is going to be 0.7 times this new velocity v, and it must equal 0.3, so the velocity here must be 1.86, meters per second. So I hope that makes sense.